For just a moment, you stand by the window of a spaceship and look down. Beyond a thin sheet of glass, a blue sphere slowly rotates. No borders, no countries, no lines on a map, only Earth, your home. From here it looks different from every map or globe. It's alive. Clouds drift, oceans shimmer, continents slide silently beneath you, and in that instant, everything becomes strangely quiet, as if all the ordinary problems of life, deadlines, news, arguments, long lines at the store, have drifted thousands of kilometers away with the planet itself, and you realize that between you and absolute emptiness there is only that thin layer of glass, thinner than it seems. Beyond it, vacuum, cold, endless darkness, while inside the ship, warmth, light, and people. A tiny pocket of life hurtling through space at tens of thousands of kilometers per hour. And right then, another realization hits you. All of humanity, our entire history, all cities, oceans, wars, music, books, billions of human lives. Everything is happening on that small sphere below you. It looks almost fragile, as though you could cover it with the palm of your hand. And then someone tells you that soon millions of ordinary people will be able to experience this moment. Not astronauts, not the chosen few. People without years of training in centrifuges, without decades of preparation. People who just yesterday were working in offices, teaching at universities, driving taxis, or building houses. Ordinary people. You, me, anyone. And the most astonishing part, it's already happening. Why does humanity even want to fly into space? There's one question I hear very often. Why go to space at all? We have so many problems right here on Earth. And you know what? It's a wonderful question, truly wonderful, because it sounds very rational. It kind of pulls us back down to the ground and forces us to look at reality without the romance. But the answer to it runs deeper than it first appears. Humans have always looked upward. This isn't a metaphor. It's literally written into our DNA. Hundreds of thousands of years ago, our ancestors lay on the grass and gazed at the stars. They didn't understand what they were. They didn't know about galaxies, about light years, about the fact that those tiny dots in the sky were actually gigantic suns, yet something inside them, something deep and primal, reached toward it, toward the unknown, toward that distant light that appeared above their heads every night and seemed to call them somewhere. That pull never disappeared. It simply became more shaped, more concrete. First, people started inventing stories about constellations. Then they learned to tell the seasons and travel directions by the stars. Then they built observatories, drew maps of the sky, calculated planetary orbits. Over time, humans began giving names to the stars. Then building telescopes. Then rockets. And every step in that direction was not merely a technical achievement. It was the fulfillment of some ancient promise that humanity made to itself. But there's one more reason that people talk about less often. It's a bit uncomfortable, but extremely important. Earth is not eternal. I don't mean the planet will die tomorrow. No. By human standards, our world is quite stable. But if you look at the 4.5 billion years our planet has existed and try to imagine the next billions, it becomes obvious. Catastrophes happen. Sometimes slowly, sometimes suddenly. Asteroids fall. Volcanoes erupt. Continents shift. Climate changes. Sometimes these processes take thousands of years, and sometimes just a few days that change everything. And if we keep all our eggs in one basket, that is, if all of humanity lives only on one planet, then one serious hit could wipe us all out in a matter of years. Elon Musk, the founder of SpaceX, the company that is literally rewriting the rules of space travel right now, says this very bluntly. He believes humanity must become a multi-planetary species, not as an ambition, but as an insurance policy, as a survival plan. Does it sound a little scary? Maybe, but think about this. You don't walk around every day thinking my house might burn down today, yet you still have insurance. That's what Musk is saying. Let's do the same thing for humanity, just on a slightly bigger scale. But let's return to things that feel closer and more tangible. Because space travel isn't only about species survival. It's also about something far more human. But to understand why this desire became so powerful, we need to go back to the moment when humanity first actually reached space. The moment when a small metal sphere changed the entire course of history. Let's travel back for a moment to the year 1957. Picture this. A cold autumn October, the Soviet Union, somewhere in the vast steppes of Kazakhstan, in absolute secrecy, they rolled a rocket up to the launch pad. All around, military personnel, engineers, people bundled in thick coats. Most of them understood they were part of something enormous, but none of them fully grasped how it would change the world forever. At the top of the rocket sat a small metal sphere, the size of a basketball, with 4 thin antennas, and inside, a simple radio transmitter. On October 4th, 1957, the rocket lifted off, and that little sphere, Sputnik 1, became the first artificial object to reach Earth orbit. It circled the planet and broadcast a simple signal. Beep, beep, beep. The whole world heard that sound, and it changed everything. America was in shock.
It's just static. I can't get a clear signal.
But what is that sound?
That, I'm afraid, is the sound of the future.
Real, genuine shock. The government, the military, the public, everyone suddenly realized the Soviet Union was already in space, and we were not. And if they could launch a satellite, they could also launch a rocket with a nuclear warhead straight at American cities. That was how the space race began.
Future belongs to those who dare to reach for the stars.
One of the most dramatic and insane competitions in the history of humanity.
We must win the space race, not because it is easy, but because it is vital to the security of the free world.
The next 12 years felt like the wildest technological sprint the world had ever seen. In 1961, Yuri Gagarin became the first human in space. His flight lasted only 108 minutes, but those 108 minutes forever divided human history into before and after. Then came the first spacewalk, the first woman in space, the first docking of 2 spacecraft, and finally, on July 20th, 1969, Neil Armstrong set foot on the moon and spoke the words that would be quoted forever. That's one small step for man, one giant leap for mankind. But here's what's interesting. After that triumph, after America won the race, the pace slowed down. The Apollo program ended. The space shuttles flew, but without the wild enthusiasm of the 60s. For decades, it seemed as though humanity had reached its peak and simply stopped. And then a new player stepped onto the stage. Several new players, actually. And they changed everything again. And then something unexpected happened. The next revolution in space would come not from governments, but from entrepreneurs. There's a concept called a tipping point. It's that moment when something that seemed impossible suddenly becomes obvious, when the rules of the game change so radically that the old players can't keep up. At first it looks like a strange idea, almost like a reckless gamble. Most people just shrug and say, that can't happen. But then a few years pass, and suddenly everyone realizes the world is already different. In the space industry, that tipping point had a specific date, September 28, 2008. That was the day SpaceX's Falcon 1 rocket finally reached orbit on its 4th attempt. the first 3 flights had failed. One rocket exploded almost immediately after launch. Another lost control. The third couldn't achieve the required speed. For any large government program, that would have been painful but not fatal. Budgets are enormous. But for a small private company, it could have meant the end. SpaceX had spent almost all its money. Engineers worked through the nights. The team literally lived at the launch site. Elon Musk later said that at that point the company had just enough left for one more launch. If the fourth one had failed too, SpaceX simply would not have existed anymore. A lot of employees understood that. And that's why the tension during that launch was almost physically palpable. But it didn't fail. Falcon 1 rose into the sky, gained speed, separated its stages, and for the first time in history, a private rocket successfully reached orbit. In mission control, people literally jumped out of their seats. Some shouted, some laughed, some just sat in silence, trying to process what had happened. And from that day, a new era began, an era in which governments are no longer the sole masters of space. Why does this matter so much? Let's break it down. Before private companies appeared, space programs cost governments insane amounts of money. Launching a single space shuttle cost roughly $1.5 billion. These were complex machines built by thousands of engineers, with dozens of safety systems and an enormous amount of manual work. Every flight was almost a unique project. For comparison, today SpaceX launches a Falcon 9 rocket for $67 million. That's 22 times cheaper. And Falcon Heavy, one of the most powerful rockets in the world, costs only $97 million. The difference is colossal, and it changes everything. When a launch costs billions, they happen very rarely. When it costs tens of millions, they can happen much more often. That means more satellites, more research, more experiments. Space gradually transforms from an extremely expensive and rare project into infrastructure. How did they do it? The answer in 2 words: reusability. It sounds simple, but behind it are years of research and thousands of failed attempts. Imagine before, a rocket would lift off, deliver its payload to orbit and fall into the ocean or burn up in the atmosphere. Single use. Like a syringe you throw away after one injection. It's a bit like if every airplane after one flight simply fell into the ocean. Impossible to imagine modern aviation under those conditions. But that's exactly how the space industry worked for decades. SpaceX did what was considered technically impossible. They taught the first stage of the rocket to return and land vertically. On its legs, right on a landing pad, or on a platform in the middle of the ocean. The early attempts looked dramatic. Rockets fell over, exploded, flipped just seconds before touching down. The internet back then joked that SpaceX had created the world's most expensive fireworks show. But every failed launch provided new data. Engineers analyzed it and tried again, and one day it worked. The first time I saw video of that landing, I watched it 20 times in a row. It's impossible to describe in words. A massive metal tube falling from the sky, slowly rotating, igniting its engines, and like something out of a science fiction movie, gently descending onto 3 legs with absolutely perfect touchdown. A cloud of steam and dust rises around it. The engine shut down, and the rocket just stands there, intact, ready to fly again. It looks like special effects, but it's reality. Besides SpaceX, other players have entered the game. Jeff Bezos's Blue Origin, Richard Branson's Virgin Galactic, Rocket Lab from New Zealand, United Launch Alliance, and dozens of smaller startups around the world. Some of them launch small rockets for mini satellites. Others work on new engines, space stations, or even future lunar bases. And this is another new feature of modern space. It's no longer a monolith. It's already a whole ecosystem of companies, engineers, and ideas that compete with each other while at the same time pushing toward the same goal, making space more accessible. All these breakthroughs raise a natural question. If space technology has changed so dramatically, then where exactly do we stand today? To understand where we're heading, we first need to clearly see where we stand. And the truth is, we live in a very strange moment in history. On one hand, humans have been flying into space for more than 60 years. On the other hand, everything happening right now feels as though the space age is only just beginning. The situation in the space industry looks like this. The International Space Station, the ISS, has been orbiting for more than 25 years. Construction began back in 1998 when the first module was launched into orbit. Since then, the station has been gradually assembled directly in space, module by module, section by section. Astronauts performed spacewalks, connected new parts, ran cables, and installed solar panels. A permanent crew of 6 to 7 people lives on board at all times. It's an international team. Astronauts from the United States, Europe, Japan, Canada, and sometimes Russia. They work there for several months at a stretch, conducting experiments, repairing equipment, photographing Earth, and every now and then simply gazing out the window. Because, they say, the view from up there is impossible to forget. The station is the size of a football field. If you look at it from the side, it resembles a strange cosmic insect. Long solar panel arrays, modules of different shapes, docking ports, antennas. Inside, there are laboratories, sleeping quarters, a kitchen, a gym, and a toilet. By the way, the most expensive toilet in the universe. It costs $19 million. And yes, astronauts are required to exercise 2 hours every day, because in microgravity, muscles and bones start to weaken. The ISS is the largest and most expensive object humanity has ever built. Its total cost is estimated at more than $150 billion. It orbits Earth at an altitude of roughly 400 kilometers, traveling at a speed of 28,000 kilometers per hour. In a single day, it circles the planet 16 times. That means the astronauts see sunrise and sunset about every 90 minutes. In one day, 16 sunrises and 16 sunsets. But the ISS already belongs to the old space era. It was a symbol of cooperation after the Cold War, a project that brought together nations that had recently been rivals. Now the next generation is being built. China, for example, has constructed its own space station, Tiangong, and it is already operational. It is smaller than the ISS, but very modern. Chinese astronauts regularly fly there, conduct experiments, and steadily expand the program. China plans to land humans on the moon by 2030. The United States, together with its partners, is also returning to the moon through the Artemis program. This time the idea is a bit different from the 60s. Back then it was a short visit, land, walk around for a few hours or days, and fly back. Now the goal is to stay longer, to build bases, to create infrastructure, to use the moon as a staging point for future deep space missions. And if everything goes according to plan, in the next 10 to 15 years, humans may once again walk on the surface of the moon and do it regularly. Meanwhile, SpaceX is building something that takes your breath away: Starship. This is the largest rocket in the history of humanity. It stands 120 meters tall. That's like a 40-story building. If you placed it next to the Statue of Liberty, it would be significantly taller. It can lift more than 100 tons of payload to orbit. For comparison, the Saturn V, which sent astronauts to the moon, could lift 130 tons, but it cost hundreds of times more and was not reusable. Starship is fully reusable. Both stages return and can be used again. The concept is almost insane. Launch the rocket, send payload to space, then catch the giant booster back with special arms on the launch tower. In April 2023 and November 2023, the first test flights took place. They were dramatic. The rockets exploded, lost control. But each launch gave engineers new data. The fourth test in 2024 demonstrated successful return of both stages. That is revolutionary. Musk plans to use Starship for lunar missions, under contract with NASA, and for flights to Mars. The first uncrewed missions to Mars could happen as early as the late 2020s. If that occurs, it will be the first step toward humanity becoming an interplanetary species. But there is something else that gets talked about less, yet might change our everyday lives even more than the moon or Mars. Satellite internet. SpaceX has already deployed Starlink, a network of thousands of small satellites in low Earth orbit. They fly at an altitude of roughly 500 to 600 kilometers and form a massive network that covers the entire planet. These satellites move across the sky in little trains. Sometimes you can even see them with the naked eye, a thin chain of bright dots slowly drifting across the night sky. They provide high-speed internet in virtually any location on Earth. Even in the middle of the ocean, even in Antarctica, even in your village if you don't have wired connection. And this doesn't just change convenience. It changes economics, education, healthcare, communication in remote regions, the work of rescue services, and even how militaries operate. This is already reality, not the future. Reality. But when we talk about giant rockets, missions to the moon, and future colonies on Mars, it's easy to forget something surprisingly simple. How does a rocket actually work? Let's pause for a minute and talk about how all of this actually works. Because honestly, when I first started getting interested in space, I didn't understand even the most basic things. A rocket takes off. Okay. It flies into space. Got it. But how exactly does it happen? Why doesn't it just fall back down? Why does it have enough power to lift hundreds of tons of metal? And most importantly, why does the whole thing look so incredibly complicated? And nobody ever explained it to me simply. So let's try to figure it out without formulas or fancy terms. So, how does a rocket actually rise into space? We'll start with the simplest thing, Newton's law. You've probably heard it. For every action, there is an equal and opposite reaction. It's one of the most fundamental laws of physics. That's exactly how a rocket works. It shoots gas downward at insane speed, and that gas pushes the rocket upward. Those gases are the result of burning fuel inside the engine. The temperature there reaches several thousand degrees. Fuel and oxidizer mix, ignite, create a powerful stream of superheated gas that blasts out of the nozzle at several kilometers per second. And all that energy pushes the rocket upward. Imagine this. You're standing on ice skates holding a heavy rock. If you throw the rock forward, you yourself slide backward. A rocket does exactly the same thing. Except instead of a rock, it continuously throws superheated gases out of its engines, not just once, but millions of times per second. Now the harder part, why can't a rocket simply fly to space the way an airplane does? Because space isn't just really, really high up. It's also really, really fast. Most people picture space like a very tall mountain, as if you just need to climb high enough. And you're there. But in reality, the main difficulty isn't the height. The main difficulty is the speed. Here's something very few people know. Reaching orbit isn't just about lifting something upward. It's about lifting something upward and accelerating that something to such a speed that it keeps falling around Earth forever without ever hitting the ground. Sounds weird? Let's picture it. You're standing on top of an extremely, extremely tall mountain, and you throw a rock horizontally. It flies a bit and falls. Throw it harder. It flies farther before falling. Even harder, even farther. Now imagine you throw it so hard that while the rock is falling downward, Earth has time to curve underneath it. And the rock never hits the ground because the surface of Earth keeps slipping away downward at exactly the same rate the rock is falling. That is orbit. Constant falling around Earth. To reach orbit, you need to accelerate to roughly 28,000 kilometers per hour. For comparison, the fastest airplane in the world, the SR-71 Blackbird, flies at about 3,500 kilometers per hour. So to reach orbit, you need to fly 8 times faster than the fastest airplane, and most of a rocket's energy goes exactly into that acceleration. That's why rockets are so huge. The vast majority of their mass is fuel. Fuel for acceleration, fuel for lift, fuel to keep thrusting. Sometimes more than 90% of a rocket's entire mass is fuel. It's like if your car weighed 90% fuel tank and only 10% everything else. Engine, seats, wheels, and body. That's why rockets have stages. When the fuel in the first stage runs out, it simply separates and falls back to Earth. The rocket becomes lighter, and the next stage can accelerate it even faster. This happens 2 or 3 times during a single launch. But there's one more problem: the atmosphere. The first few kilometers of ascent are the hardest. Air creates drag, slows the rocket down, heats up its skin. At speeds of several thousand kilometers per hour, even air becomes almost like a solid barrier. That's why the first minute of flight is the most dangerous. Engines run at maximum, skin temperature skyrockets. The structure experiences insane forces. Vibrations are so strong that astronauts sometimes describe it as riding inside a metal earthquake. This moment even has a special name among rocket engineers: Max Q. It's the point where the combination of speed and atmospheric density creates the maximum aerodynamic load on the rocket's body. If the rocket survives that moment, things get much easier afterward. Because then, above 80 to 100 kilometers, the atmosphere basically ends. Almost no drag, no air to slow it down. And the rocket can freely hurtle at its insane speed through open space. The engines are still firing, but now almost all their energy goes into acceleration instead of fighting air resistance. Here's what's mind-blowing about all of this. All this physics was figured out by Newton back in the 17th century. He calculated orbits. He explained gravity. He gave the formulas. Legend says the idea of orbit came to him when he imagined a cannon on top of a mountain firing harder and harder until the cannonball starts circling Earth. Humanity simply didn't have the technology to apply that knowledge. It took another 300 years, and paradoxically, 2 world wars for rocket technology to mature to the required level. So now imagine the rocket has done its job. The engine shut down. The acceleration disappears. And suddenly something very strange happens. Okay, the rocket has launched. You're in orbit, and that's when something begins that no amount of preparation can fully ready you for. Even years of training, centrifuges, and parabolic flights with short bursts of weightlessness, all of that is just an approximation. The real experience is always different. Weightlessness. It sounds romantic, doesn't it? You're floating, drifting through the air, like a character in a cartoon. In videos from space stations, astronauts smile, push off walls, flip in midair, juggle apples. In reality, the first few hours of weightlessness are a disaster for your body. First, your stomach, your vestibular system, the balance mechanism in your inner ears, suddenly stops receiving proper signals. On Earth, it constantly senses down because gravity pulls fluid in your inner ear in a specific direction. In space, that signal disappears. It screams, "You're falling." But there is no falling. Your brain gets confused. The result, nausea. Roughly 70% of astronauts experience space sickness in the first days. It's similar to seasickness, except you're also wearing a spacesuit inside a tiny module with nowhere to escape. Some astronauts admit honestly, for the first few days they just try not to move any more than necessary. Second, blood. On Earth, gravity pulls blood downward toward your legs. In weightlessness, that doesn't happen. Blood distributes evenly throughout the body, and a significant portion of it rises straight to your head. For the first few days, astronauts feel constant nasal congestion and a sensation of fullness in the head, as if they're permanently leaning forward. Their faces swell, their legs get thinner. This even led to a term, moon face and bird legs. The upper body looks slightly puffy, while the legs appear noticeably thinner. It may sound like a minor detail, but it's extremely uncomfortable. Third, muscles and bones. Without gravity, the body doesn't receive the load it's accustomed to. On Earth, even the simple act of standing forces dozens of muscles to work. In space, none of that happens. Muscles begin to atrophy within just a few days. Bones lose density. Astronauts who spend 6 months on the ISS can lose 1 to 2% of bone density during that time. That's roughly the amount an elderly person might lose in a year on Earth. That's why they exercise every single day, 2 hours of mandatory workouts to slow this process. The station has special treadmills with harnesses, stationary bikes, and even resistance machines that work on vacuum principles. Without this routine, an astronaut returning to Earth wouldn't even be able to walk properly. But there are things astronauts talk about with unmistakable awe. Silence in space. It's true silence, not the kind we call silence on Earth, when you can still hear your own breathing, a distant car, the rustle of leaves. Real, absolute silence. Sound doesn't travel in a vacuum. If you step out into open space, there is no sound at all. Even if an engine is firing right next to you or something massive explodes, you won't hear it. Everything is transmitted only through the structure of the spacesuit or via radio. For many astronauts, this is one of the strangest moments. Sunrise every 90 minutes. The ISS orbits Earth 16 times a day. That means 16 sunrises and 16 sunsets every 24 hours. Astronauts describe the first sunrise like this. At first, the horizon begins to lighten slightly, a thin strip of blue. Then that strip grows brighter, more yellow, and then suddenly, in just a few seconds, it explodes into full sunlight. And this happens 16 times a day. And then there's what astronauts often call the most powerful experience of their lives, the overview effect. There is a term in English, overview effect. It's a psychological phenomenon described by almost every astronaut who has seen Earth from space. Suddenly you understand, not just think, but feel it deep in your gut, that the lines on maps are meaningless, that there is no ours and theirs continent, that the borders which seem so important on political maps don't exist at all, that all of humanity lives on that same tiny sphere hanging in black emptiness, and that this sphere is unbelievably fragile. Most astronauts return to Earth as different people, calmer, more oriented toward global thinking, less bothered by petty everyday conflicts. You could say, space cures limited thinking. Once humanity learned how to reach orbit, another question naturally appeared. If we can stay in space, where should we go next? More than 50 years have passed since the day Neil Armstrong stood on the surface of the moon. 50 years! And for all that time, humans haven't gone back there. Why? The short answer: after America won the race and the moon proved that the United States was technologically ahead of the Soviet Union, the political motivation vanished. Congress slashed the budget. The Apollo program was canceled after Mission 17. Flights to the moon were extraordinarily expensive. Every mission required a gigantic rocket, thousands of engineers, and years of preparation. Once the main political goal was achieved, interest gradually faded. But now the situation is changing. NASA has launched the Artemis program with the goal of returning humans to the moon. And this time it's not just about stepping around and coming back. The goal is to build a permanent base to stay. The first unscrewed flight, Artemis 1, took place in 2022. The Orion spacecraft flew around the moon and returned to Earth successfully. In 2024, Artemis 2, the same route but now with a crew. And Artemis 3 is planned to be the first human landing on the moon since 1972. And for the first time in this mission, there will be a woman on the moon. And for the first time, a representative of a racial minority. But NASA is not the only player. China, as I mentioned earlier, is also actively working on its lunar program. And this is once again igniting the spirit of competition. History shows when major powers start competing in space, progress accelerates dramatically. But why return to the moon at all? Just to plant a flag? No. There are far more reasons. The first reason, ice in the craters. On the moon, in the shadows of the polar craters, where sunlight never reaches, there is water in the form of ice. This was discovered back in the 1990s, but confirmed with much greater precision in recent years. And this water is the most valuable resource in the solar system if you want to live there or travel farther. Water can be drunk, plants can be grown with it, but most importantly, water can be split into hydrogen and oxygen through electrolysis and used as rocket fuel. Imagine, instead of hauling all your fuel from Earth, which is expensive and heavy, you extract fuel right on the moon. And the moon becomes a gas station for flights deeper into the solar system. The second reason, helium-3. There is an isotope called helium-3. On Earth, it is almost non-existent, but on the moon, it exists, and it could potentially serve as fuel for thermonuclear reactors. If we ever learn how to build them, 1 ton of helium-3 could theoretically provide as much energy as 40 million tons of coal, with no radioactive waste. It's clear why everyone suddenly became so interested in the moon. The third reason, and possibly the most important for the long-term future, the moon is a launch pad. The moon's gravity is 6 times weaker than Earth's. To launch a rocket from the moon requires 6 times less energy than from Earth. But the moon is only the first step. For decades, scientists and engineers have been thinking about a much more ambitious destination. Yet at the same time, to what people understand the least, Mars. Elon Musk wants to send humans to Mars, and not just send them and bring them back the way it was with the moon missions. His plan is far bolder. He wants to build a city there, self-sufficient, independent, one that could survive even if contact between Earth and Mars were suddenly cut off. And he talks about something extremely ambitious. 1 million people on Mars within 1 human lifetime. Does that sound like science fiction? Perhaps. But let's break down how truly unrealistic it really is. And we'll start with an unexpected fact. Mars is not as terrifying a planet as it first appears. Yes, there is not enough oxygen there. The atmosphere consists mostly of carbon dioxide. A human cannot breathe it, but that gas is not only a problem, it can be used as a resource. Oxygen can be produced from it, and even rocket fuel. Yes, it is very cold there. The average temperature is roughly minus 60 degrees Celsius. That's about like an Antarctic winter, except without a warm ocean nearby. Another problem, pressure. Atmospheric pressure on Mars is so low that it resembles conditions at an altitude of roughly 35 kilometers above Earth. For comparison, passenger airplanes fly at about 10 to 12 kilometers, so even the lower layer of Mars's atmosphere is almost completely uninhabitable. But there is good news too. A day on Mars is almost the same as on Earth. It lasts roughly 24 hours and 37 minutes. This Martian day even has its own name, a soul. Gravity there is roughly a little more than 1/3 of Earth's, about 38%. That is significantly less than on Earth, but still much more than complete weightlessness in space, so people could walk, work, and move around relatively normally. And there is one more important thing. There is water on Mars, not in the form of rivers or oceans, but as ice, at the poles and likely beneath the surface of the planet. There are also useful resources: iron, silicon, basaltic rocks. So in short, Mars is hard for life, but not hopeless. Yet the main difficulties begin exactly where most people don't even think about them. The first problem: the journey. Mars is between roughly 55 and 400 million kilometers from Earth. It all depends on exactly where the planets are in their orbits around the Sun at that moment. And there is one more nuance. The ideal launch window opens only about once every 26 months. That is when the trajectory between the planets requires the least energy, even under the best conditions. The trip takes roughly 6 to 9 months. Think about that for a second. Half a year. Sometimes almost a full year. In a small spacecraft, a lot happens during that time. Muscles begin to weaken. Bones lose calcium. The psyche feels pressure from isolation and confined space. But the most dangerous thing: radiation. On Earth, we are protected by the planet's magnetic field. It deflects most of the charged particles flying in from space. Even the International Space Station is still inside that protective field. But between Earth and Mars, almost nothing. Cosmic rays and solar flares can damage cells, DNA, and the nervous system. That is why radiation shielding is one of the most critical issues in modern space engineering. Now the second problem: landing. And here, Mars has prepared a very strange trap for engineers. Its atmosphere is about 100 times thinner than Earth's. And that creates a paradox. It is dense enough for a spacecraft to heat up dramatically during entry, but not dense enough for parachutes to effectively slow down a large ship. Engineers even joke that Mars is the planet with an atmosphere that is just inconvenient enough to be possible. So the landing looks roughly like this. First, the spacecraft enters the atmosphere with a heat shield. Then giant parachutes deploy. And at the very end, rocket engines fire to kill the final speed. That is exactly how the Starship is planned to land. First, it brakes using the atmosphere, then falls almost horizontally, and at the last moment flips over and lands on its engines, almost like in old science fiction movies. The third problem: where to live. The surface of Mars is not particularly friendly to life. Strong ultraviolet radiation, very cold nights, and dust storms that sometimes engulf the entire planet. Such storms can last for months, and Martian dust is extremely fine and sticky. It can get almost everywhere and gradually ruin equipment. That is why the first colonies will most likely not be on the surface, but beneath it. Underground bases, tunnels, or natural lava tubes could serve as natural shields against radiation. There is also another option: inflatable modules covered with a thick layer of Martian regolith. It doesn't sound very comfortable. But remember the first settlers in North America. Their first houses were also very far from comfortable. And finally, the most important problem: self-sufficiency. If something breaks on the International Space Station, Earth is just a few hundred kilometers away. A new part can be delivered in a few hours. On Mars, everything is different. The minimum return trip, roughly half a year, and a radio signal between the planets can take anywhere from a few minutes to almost 3/4 of an hour. That means one very simple thing. If something goes wrong, the colonists must solve the problem themselves, without quick help from Earth. That means on Mars it will be necessary to create a small civilization, systems for producing oxygen, water recycling, growing food, medicine, manufacturing parts, energy, essentially a full-fledged human society. On another planet, a ship for a flight to Mars, it is much cheaper and simpler to assemble and launch it from the moon than from Earth. Yet even Mars may not be the final frontier, because once humanity learns to live on more than one planet, a much bigger question appears. The moon, that's impressive. Mars, even more so. But there are people for whom that's not enough, and honestly, I'm one of them. Because the real question sounds different. What lies beyond? Beyond our solar system. The closest star to us is Proxima Centauri. It is located at a distance of roughly 4.24 light years. And here it's worth explaining one important thing. A light year is not a measure of time. It is a measure of distance. It is the distance that light travels in 1 year at a speed of roughly 300,000 kilometers per second. If we convert that into familiar numbers, 1 light year is approximately 9.5 trillion kilometers. And the distance to Proxima Centauri is roughly 40 trillion kilometers. Now let's look at our real capabilities. The fastest spacecraft humanity has ever launched is the Voyager 1 probe. It is traveling at roughly 17 kilometers per second. That sounds fast, but there is a problem. If we were to fly to Proxima Centauri at that speed, the journey would take roughly 75,000 years. 75,000 years. That is longer than modern civilization has existed. So with our current technology, travel to other stars is practically impossible, at least within a single human lifetime. But scientists are already thinking about other ways. Idea number 1, the Breakthrough Starshot project. The concept sounds almost like science fiction. Tiny probes, about the size of a postage stamp, equipped with ultra-thin light sails. Powerful lasers from Earth would shine on these sails and literally push them with light. Light carries momentum, and if the laser is powerful enough, it could accelerate the probe to roughly 1/5 the speed of light. In that case, the trip to Proxima Centauri would take roughly 20 years. Not thousands, 20. And that already sounds almost realistic. Idea number 2, the warp drive. It was proposed by physicist Miguel Alcubierre. The essence is very strange. What if the ship doesn't move faster than light? What if space itself moves? Space in front of the ship contracts, behind it expands, and the ship sits inside what is called a warp bubble. Theoretically, this model does not violate Einstein's equations. Practically, however, there is one problem. It would require so-called exotic matter, a substance with negative mass. It may not exist at all, but the idea itself is already being studied. And finally, the third possibility, wormholes, tunnels in space-time that could connect extremely distant points in the universe. If such tunnels exist, and if humanity ever learns how to stabilize them, travel between stars could take minutes. But for now, there is one small problem. No one has ever seen a wormhole. They exist only in mathematical equations. But the history of science shows one interesting thing. Sometimes the equations appear first, and reality catches up to them much later. But while scientists dream about distant stars, something much closer to Earth is already beginning to change space forever. Or rather, rise just a little bit above it. Because while scientists are thinking about Mars, interstellar travel, and the future of humanity thousands of years from now, Some entrepreneurs decided to do something much simpler. They decided to sell tickets to space. And here's one interesting thing. Space tourism is no longer a distant future. It is already happening. In 2021, two events took place that clearly showed the new era had already begun. In July, Richard Branson flew on Virgin Galactic's spacecraft called VSS Unity. 9 days later, Jeff Bezos went up to space on Blue Origin's New Shepard rocket. They were different spacecraft, different companies, but the same idea. Both flights were what are called suborbital. What does that mean? The spacecraft launches straight up vertically. It rises above 100 kilometers. That's the conventional boundary of space known as the Kármán line. After that, the spacecraft does not enter orbit. It simply starts falling back toward Earth. The entire flight lasts a short time, but there is one moment for which people pay such enormous amounts of money: a few minutes of real space. During those minutes, passengers experience weightlessness. They can unbuckle their safety harnesses and literally float inside the cabin. Through the windows, they see the black sky of space and the thin blue line of the atmosphere, and also the curvature of Earth. And many astronauts say that this exact moment changes a person forever. Now for the less poetic part, the price. A ticket on a Virgin Galactic flight costs roughly $450,000. Blue Origin does not publicly disclose the exact price, but according to various estimates, it is around the same level. Of course, right now, this is accessible only to extremely wealthy people. But the history of technology shows one interesting pattern. New technologies are always first available only to a small group of people. Then they gradually become cheaper. Think about the history of aviation. The first commercial airplane flights in the 1920s were extraordinarily expensive. A flight across the Atlantic Ocean at the end of the 1930s cost roughly the equivalent of about $9,000 today. Today, a transatlantic flight can be found for $400 or $800. The technology gets cheaper, scale increases, and prices fall. But the real revolution in space tourism is not these short suborbital hops. The most interesting part begins in orbit. SpaceX has already sent several private missions into Earth orbit. One of the most famous, the Inspiration 4 mission. It launched in September 2021. This was the world's first orbital flight with an entirely civilian crew. No professional astronauts at all. There were 4 people on board. Among them, a teacher and an oncologist doctor. They spent roughly 3 days in orbit, and they flew at an altitude of roughly 575 kilometers. That is even higher than the orbit of the International Space Station. The next step was the Polaris Dawn mission. In that flight, private astronauts performed the first spacewalk in history. Something that just 10 years earlier seemed completely impossible became reality. But for now, the price of such trips remains enormous. An orbital flight costs tens of millions of dollars. For now, there's another company that wants to change the rules of the game. Axiom Space plans to build the first fully private space station. The first modules of this station will dock with the International Space Station, and private astronauts have already visited it. One such flight cost roughly $55 million for about 10 days in orbit. It is still very expensive, but if the new Starship spacecraft starts flying regularly and dramatically reduces launch costs, the situation could change very quickly. In the 1930s of this century, orbital tourism could become accessible to the very affluent part of the middle class. And then, possibly, even to ordinary people. Elon Musk once said something interesting. The goal of SpaceX is to make humanity a multiplanetary species, but as a side effect, to give every person the chance one day to see Earth from space, and perhaps some of us will still live to see that happen. Up to this point, we have mostly talked about technology, rockets, spacecraft, colonies, but space exploration also forces us to confront something far deeper, and this time, not forward into space, but deeper into the very understanding of the universe, because there is one thing that has puzzled physicists for many decades, and that thing is called dark matter. Let's start with a paradox. We are almost certain that it exists, yet we still don't know what it is. The story of its discovery began in the 1970s. American astronomer Vera Rubin was studying the rotation of galaxies. She measured the speeds of stars in different parts of galaxies. Logic suggested something very simple. Stars closer to the center of the galaxy should move faster. Stars on the outskirts, slower, just like planets in the solar system. Mercury orbits the Sun faster than Earth. Neptune, much slower. But when Rubin looked at the real data, she saw something very strange. Stars at the edges of galaxies were moving at almost the same speed as stars near the center, and sometimes even faster. This contradicted everything known at the time about gravity. If a galaxy contained only the mass we can see, the stars on the periphery would simply fly off into intergalactic space. But that doesn't happen. Something is holding them in their orbits, something invisible, but extremely massive. That invisible something was named dark matter. Further calculations revealed something even more astonishing. Dark matter makes up roughly 27% of the entire universe. Another roughly 68% is dark energy. And everything we can actually see, stars, planets, galaxies, gas, and cosmic dust, accounts for only about 5%. Only 5. That means one very strange thing. We literally cannot see or understand approximately 95% of the universe. Imagine a science that explains only a tiny fraction of reality. That is exactly the situation modern physics finds itself in right now. And here comes the question. Why does this matter for space travel? There are several possible reasons. First, dark matter may consist of particles we have not yet discovered, and new fundamental particles sometimes mean new sources of energy. And new sources of energy, that means new engines. For now, this is only speculation, but that is exactly how most major technological revolutions begin. Second, dark matter shapes the gigantic structure of the universe, the cosmic web of enormous gravitational filaments along which galaxies form. A better understanding of this structure would help us plan future interstellar missions more precisely, and perhaps even use gravitational effects to our advantage. But there is a third reason, the deepest one. Dark matter reminds us of something very important. We often think we have almost figured out the universe. But in reality, we have only just begun to open the doors. And behind those doors, there are far more mysteries than answers, and that is precisely what makes exploring the cosmos so thrilling. Because every new discovery doesn't end the story, it only begins the next one. And once we begin to understand how vast and mysterious the universe really is, another question inevitably appears. This is a question humanity has been asking itself for millennia, and only now, for the first time in history, do we have real scientific tools to start investigating it. Is there anyone else in the universe? Let's start with the numbers. In our galaxy, the Milky Way, there are roughly 200 to 400 billion stars, and many of them have planets. The Kepler Space Telescope and other missions have shown planets are the norm, not the exception. According to astronomers' estimates, our galaxy alone may contain billions of planets located in the so-called Goldilocks zone, the region around a star where temperatures allow liquid water to exist. And in the observable universe, there are roughly 2 trillion galaxies. 2 trillion. If even a small fraction of stars in each galaxy has habitable planets, the number of potentially inhabited worlds becomes literally astronomical. And here appears the famous Fermi paradox. Physicist Enrico Fermi once asked a simple question over lunch. If the universe has so many places where intelligent life could arise, then where is everybody? Where are the signals? Where are the ships? Where are the traces of other civilizations? For roughly 60 years, we have been listening to the cosmos in search of signals from other civilizations through programs like SETI, and so far, silence. Almost silence. In 1977, a radio telescope in Ohio detected a very unusual signal. One of the researchers wrote, "Wow," next to it, and that's how the signal entered history. It lasted roughly 72 seconds and had characteristics that could match an artificial source. But the signal never repeated. There are several possible explanations for this paradox. The optimistic explanation is simple. We simply haven't looked long enough. Radio waves from our first broadcasts have spread only about 100 light years around Earth. In galactic terms, that's almost nothing. Another explanation: the distances in the universe are simply too vast. Even if civilizations exist, they may be so far apart that they never meet. There is also a more disturbing idea: the so-called Great Filter. This hypothesis suggests that in the development of any civilization there is a critical barrier that almost no one can overcome. Perhaps nuclear war, perhaps ecological catastrophe, perhaps uncontrolled artificial intelligence. And the most unsettling question here is, what if that barrier is still ahead of us, not behind? So what might the next centuries actually look like if humanity continues moving outward into space? Let's do a little dreaming. But we'll dream not blindly, but based on real scientific trends. The next 10 to 20 years, humans will almost certainly return to the moon. The first permanent lunar base will appear. Extraction of ice from polar craters will begin. The first serious missions to Mars will take place. Space tourism will become more widespread in 50 years. If technological progress continues, a permanent colony on Mars could emerge with hundreds or even thousands of people. Industrial mining of resources from asteroids will begin. The first real space hotels may appear in orbit. In n hundred years, possibly millions of people living beyond Earth. The first generations born on Mars, the first unscrewed probes sent toward other star systems. But there is one more factor that could change everything: artificial intelligence. AI is already helping NASA analyze astronomical data, discover new exoplanets, and plan space missions. In the future, it could control fully autonomous spacecraft. Imagine a ship flying toward a distant star for 1,000 years, without a crew, controlled by artificial intelligence. It arrives, builds a base, and only then do humans begin colonization. Space and artificial intelligence. They are not competitors, they are partners. In 500 years we enter the realm of pure science fiction, possibly a terraformed Mars with millions of inhabitants, stations in the asteroid belt, bases on the moons of Jupiter, the first generation ships for interstellar travel, and perhaps the first true interstellar colonies. Humanity scattered among the stars. But all of this is possible only under one condition: we must survive the next few centuries, not destroy ourselves in wars, not ruin the planet, not become afraid of our own future, because space is not merely a technological challenge, it is a test of our maturity as a civilization. But technology is only part of the story. Space exploration also changes something much deeper: the human mind itself. We've talked a lot about physics, about rockets, about planets, but there is one dimension of space travel that touches me personally the deepest, and one that is rarely discussed in popular science programs. What does space do to a person from the inside? I already mentioned the overview effect, but let's dwell on it in more detail. Edgar Mitchell, astronaut of the Apollo 14 mission, returned from the moon in 1971, but he returned a different person. He described the moment when he looked at the starry sky and suddenly felt, not with his mind, but with his whole body, that he was part of something infinitely larger, that the universe is not a cold mechanical machine, but something alive and conscious. He devoted the next decade to studying consciousness and the spiritual dimension of science. He founded the Institute of Noetic Sciences. Ron Garan, a NASA astronaut, wrote the book Orbital Perspective. He says, from orbit you see conflicts on Earth and think how absurd this is. People fight over scraps of land on a planet that, on the scale of the universe, is smaller than a speck of dust. But there is also a dark side. Prolonged isolation in a confined space is a serious psychological burden. On the ISS, they conduct very careful selection, not just physical fitness, but psychological stability, the ability to get along with people in a confined space for months. On long missions, for example to Mars, psychological problems will be one of the main threats. Monotony, being cut off from family, the impossibility of going for a walk, constant closeness to the same 4 to 6 people. NASA scientists are already modeling these scenarios. They conduct isolated missions on Earth. Groups of volunteers who live in sealed domes in the middle of the desert, recreating the conditions of a Martian mission. They observe psychological processes. They search for ways to support mental health. But there is one more psychological phenomenon that deserves attention. Let's call it cosmic melancholy. There are people, and I am one of them, who feel a deep, inexpressible sadness when looking at the starry sky. Not fear, not anxiety, but something akin to longing for a home they have never seen. Nietzsche would have called it the call of the abyss. Psychologists have a term for this, astromelancholy or cosmic longing. The feeling that a human being is too small for the universe in which they live, that our existence on this tiny planet is too limited, that there is something out there in the black void between the stars that is calling. And you know what? I think this is not a weakness. It is a sign of deep understanding. Those who feel this longing, they grasp the scale. They feel that humanity has not yet reached where it is destined to go, and this feeling, perhaps, is the most powerful engine of progress, more powerful than any rocket. Yet behind every rocket launch there is another powerful force shaping the future of space. Here we move to a topic that is often avoided in romantic stories about space. But it is extremely important if we want to honestly understand what is really happening. Who really controls space? The answer, for now, no one completely. But a serious struggle for control is already underway. The Outer Space Treaty of 1967, the treaty on principles governing the activities of states in the exploration and use of outer space, was signed by most countries. It establishes space is the province of all mankind. No country can claim sovereignty over planets, the moon, or other celestial bodies. But there is a nuance. The treaty was signed by states. It says nothing about private companies. In 2015, the United States passed the Space Act, which allows American companies to extract resources from asteroids and planets and sell them. They cannot claim sovereignty, but they can sell what they extract. Luxembourg and several other countries have passed similar laws. Russia and China protested, saying this violates the spirit of the 1967 treaty. Here is where it gets interesting. The asteroid belt between Mars and Jupiter is literally untold trillions of dollars in metals, platinum, gold, nickel, iron in quantities that are hard to even imagine. Just one asteroid, 16 Psyche, is estimated to contain more metals than all the metal reserves on Earth combined. Whoever gains access to this first gains not just money, They could change the entire global economy. And the moon? The same helium-3, the same reserves of ice at the poles, potential gas stations for interplanetary ships. Whoever controls these resources controls the roadway into the solar system. That is why more and more countries are not just interested in the moon for scientific reasons. India, the UAE, Japan, Israel, all have sent missions. China plans a permanent base. The United States wants the Artemis program. This is not just science. This is geopolitics. But on an entire sky higher, there is another troubling trend, the militarization of space. Several countries, the United States, Russia, China, India, have conducted tests of anti-satellite weapons. They have shot down their own satellites with missiles, demonstrating the ability to blind an adversary's satellite systems. More and more countries understand whoever controls orbit controls information, GPS navigation, communications, military advantage. Space has ceased to be a neutral space. It is becoming an arena of struggle. But I want to end this section on a non-pessimistic note. The ISS is the longest international project in space. For 25 years, Americans, Russians, Japanese, and Canadians have lived and worked there together. Even during the worst periods of relations between the United States and Russia, astronauts and cosmonauts continue to perform spacewalks side by side. Space has shown when there is a common goal, people can come to an agreement. Even those who pound their fists on the table during diplomatic negotiations down below, perhaps this is the most important lesson we have received from the space program. All these grand ideas about the future can make us forget something remarkable. Have you ever wondered what a regular Monday looks like when you live in orbit? You wake up at 6 in the morning. But morning is just a convention, because outside the window it's dark and bright and turns every 45 minutes. The alarm clock isn't about the sun rising. It's simply because that's what Mission Control in Houston decided. The first thing you do is not drink coffee. First, system checks. Is the pressure in the module normal? Oxygen levels? Carbon dioxide concentration? On the ISS, everything is monitored automatically. But astronauts manually verify the data every morning. Because if something goes wrong, you need to know immediately. After the checks, hygiene, and that's where the fun acrobatics begin. There is no shower on the ISS in the usual sense. There are wet wipes and special no-rinse shampoo. You wet the wipe, clean yourself, and you're done. You brush your teeth with special toothpaste that you can swallow, because there's nowhere to spit the water. In weightlessness, it would scatter in droplets throughout the module and get into the ventilation. The toilet deserves its own story. It works on a vacuum principle. Suction pulls everything extra away, because without gravity, well, you understand. Liquid waste is collected and recycled into drinking water. Yes, you read that correctly. The ISS has a water regeneration system that recycles everything, including sweat and urine, back into potable water. Technically, this water is cleaner than most tap water on Earth, but psychologically, every new astronaut takes some time to get used to it. Breakfast comes from tubes or vacuum-sealed pouches, specially developed food that doesn't crumble. Tiny crumbs in weightlessness can get into eyes, nose, or worst of all, into electronic equipment and short-circuit something. That's why there is no regular bread on the ISS. Instead, special flatbreads that don't produce crumbs. Coffee is a special point of pride. NASA, together with SpaceX, developed a special space espresso. Coffee in capsules, drunk through a straw from a special pouch. The first real Earth-like coffee arrived on the ISS only in 2015. The iEspresso machine became a genuine sensation for the crew. After breakfast, the morning briefing. This is a video conference with Mission Control in Houston for the American segment and in Moscow for the Russian segment. Discussion of the day's plan, technical issues, crew health status, and then work. Most of the time, astronauts on the ISS are conducting scientific experiments. Hundreds of studies in physics, biology, material science, medicine, all of them take advantage of the unique conditions of microgravity, conditions impossible to replicate on Earth. For example, crystals of certain proteins grow much cleaner and larger in weightlessness than on Earth. This allows scientists to study their structure and develop new medicines. Some medical breakthroughs of recent decades are a direct result of research on the ISS. Or combustion in microgravity behaves differently. Flames don't rise upward, they form a perfect sphere. Studying this has helped develop more efficient and environmentally friendly engines for cars. At 1 o'clock, lunch. At 2 o'clock, free time. Yes, there is free time on the ISS. Astronauts read books, watch series, there is internet access. Slower than at home, but it exists. Call their families. Scott Kelly, the American astronaut who spent nearly a year on the ISS, often posted photos of Earth from the window. Those images became a sensation on Instagram. At 2:30 a mandatory exercise, 2 hours every day. Specialized equipment, a treadmill with harness straps so you don't float away, a cycle ergometer, a resistance device that simulates weightlifting using vacuum cylinders. At 5:30 dinner, at 9:30 lights out. Astronauts sleep in sleeping bags attached to the wall. Without that, you would simply float around the module during sleep. Some astronauts say the first month they couldn't sleep properly. The brain didn't understand where down was and kept expecting to fall. Over time, you get used to it. And one more detail that amazes everyone, the windows. On the cupola module of the ISS, there is a 7-pane glass window, a panoramic porthole. Astronauts say there is always a line to it, especially during passes over cities at night, the lights of New York, the lights of Tokyo, the flicker of lightning over tropical storms, the night lights of Egypt along the Nile. A thin golden thread in the darkness. Auroral clouds over the poles, shimmering green and pink. That alone is worth flying into space. Just for that. But as human activity in orbit grows, another reality becomes impossible to ignore. I already touched briefly on the militarization of space, but it is so important and so rarely discussed publicly that it deserves a separate, honest conversation. Let's start with a fact. Space has never been completely peaceful. The first satellites, both American and Soviet, were closely tied to military programs. The launch rockets that sent them into orbit were modified ballistic missiles. Reconnaissance satellites were spying on adversaries from orbit as early as the 1960s. GPS, the system you use every day for navigation, was developed by the U.S. Department of Defense. Originally for guiding missiles and coordinating military operations. In other words, space and military technology have been Siamese twins from the very beginning. But now the situation is intensifying. In November 2021, Russia conducted a test. It launched a missile and destroyed its own old satellite Cosmos 1408 in orbit. A cloud of thousands of debris fragments was created. Astronauts on the ISS, including the Russian ones, had to shelter in docked spacecraft for several hours in case of collision. This was not just a technical test. It was a message. We can blind your satellites. China conducted a similar test back in 2007. The United States, in 2008, satellites are not just technology. They are critical infrastructure. GPS navigation, satellite internet, military communications, meteorology, financial transactions. Take out the right satellites. and a large part of modern civilization grinds to a halt. That is why China and the United States are now actively developing not only spacecraft but also space weapons. Laser systems capable of blinding satellite optics, kinetic interceptors, missiles that destroy satellites, parasite satellites, devices that approach foreign satellites closely and can damage or capture them. In 2019, the United States officially created the Space Force, the sixth branch of the armed forces. China has a similar command. But there is a paradox. If a space war breaks out and enough satellites are destroyed, the Kessler effect will occur. A situation in which a debris cloud in orbit becomes so dense that new collisions generate even more debris, which generates even more collisions, and orbit becomes inaccessible to anyone for decades or centuries. In other words, whoever wins a space war may simultaneously deprive all of humanity of access to orbit for generations. That is a murderous victory. That is exactly why diplomats from different countries are now seriously discussing a treaty on non-aggression in space. So far without concrete results. But the discussion is ongoing, and here's what is important. Ordinary citizens rarely know about these negotiations, rarely think about the fact that all the conveniences of the modern world depend on a few thousand objects circling above our heads, and that these objects are extremely vulnerable. Space is not only romance and science, it is a new front for human conflicts. And how we handle this will determine a very great deal. And not all the dangers of space come from geopolitics. There is one topic that people don't like to mention in exciting stories about space, because it's a bit embarrassing, but extremely important. We have littered orbit. This is not an exaggeration. Today, more than 27,000 tracked objects of space debris are orbiting Earth. Defunct satellites that no longer work, spent rocket stages, fragments from collisions, lost tools from spacewalks, even frozen droplets of coolant fluid. But that is only what we can track. Objects larger than 10 centimeters. If we count smaller pieces, fragments from 1 to 10 centimeters, there are roughly 500,000 of them. And smaller than 1 centimeter, millions. Oh, what's the big deal? They're tiny, one might think. But here is the problem. These objects are moving at 7 to 8 kilometers per second. For comparison, a bullet from a pistol travels about 1 kilometer per second. So even a 1 centimeter piece of debris hits with energy 50 times greater than a pistol shot. The ISS regularly performs debris avoidance maneuvers. It changes orbit to avoid collision with tracked debris. From 1999 to 2023, it did this more than 30 times. Astronaut spacesuits are also designed to withstand impacts from microparticles, but every spacewalk carries risk. Not huge, but real. And the situation is getting worse. Why? Because right now we are launching more and more objects into space. Starlink, just the first phase, means 12,000 satellites. OneWeb, Amazon Kuiper, and dozens of other companies are also deploying their networks. By 2030, there could be tens of thousands of active satellites in low Earth orbit. And when collisions start happening between them, clouds of debris form. Solutions are being sought. Several startups and agencies are developing orbit cleaners, spacecraft that capture debris, with nets, magnets, harpoons, and deorbit it, clear space. The Japanese company Astroscale, ESA, all of them have already launched or are preparing demonstration missions. But the most important thing is prevention. New satellites are already being designed with active deorbit capability after their mission ends. International standards require that a spacecraft in low orbit be deorbited into the atmosphere within 25 years after failure. 25 years is still too long. Some propose shortening it to 5. This is not just a technical problem. It is the first test of whether humanity can behave responsibly in a new environment. We failed this test on Earth, in the oceans, in the atmosphere. Will we repeat the same mistake in space? The answer depends on the decisions being made right now, on the laws being written right now, and on how much attention we, as a society, pay to this issue. And once we seriously talk about living on another planet, one surprisingly simple question appears. Here is a question that is rarely asked, but which is absolutely central to any serious Martian mission. What will these people eat? Hauling food from Earth? Impossible in the long term, even if Starship makes delivery much cheaper. The logistics between two planets separated by at least 6 months of travel simply do not allow dependence on an Earth supermarket. So food must be grown on site. But how? Mars is not a place for picnics in the fresh air. First, Martian soil is toxic. It contains perchlorates, salts of perchloric acid, which in the concentrations found in Martian regolith are deadly to most plants and to humans. No potato planting in the style of the movie The Martian, at least not without prior treatment. But perchlorates can be removed. Certain species of bacteria eat perchlorates. Simple water washing also helps. After treatment, Martian regolith, the soil-like material, could theoretically serve as a base for growing plants if organic matter and necessary micronutrients are added. Second, radiation. On the surface of Mars without magnetic field protection, radiation levels are roughly 50 times higher than on Earth's surface. It is not immediately lethal, but the impact on plants is significant. Solution: underground farms, or farms under shielded domes, or inside rock cavities. Third, lighting. Mars is farther from the sun. It receives roughly 43% of the sunlight Earth gets. For some plants, that is not enough. Artificial lighting is needed, and a significant amount of energy. But all of these are solvable problems, and scientists are already working on them. NASA has the Advanced Plant Habitat Program, growing plants on the ISS. They have successfully grown lettuce, radishes, chili peppers, onions. Astronauts ate these plants the first time in 2015 when they picked and ate the first portion of space-grown lettuce. There is another approach, and it could be revolutionary. Microalgae and bacteria. Some microorganisms are exceptionally efficient. They convert K-quos, AECA, and sunlight into protein and fats. Spirulina, for example, a microalga that is 60 to 70% protein and contains all essential amino acids. It grows very quickly, under relatively simple conditions, and requires minimal resources. If you add crickets or other insects, another source of protein with very efficient feed to nutrient conversion, a Martian diet could be quite balanced. Sounds strange? But the first Martian colonists will most likely eat mainly plants, algae, and insects, and over time, lab-grown meat. The technology for cultivated meat, without slaughtering animals, is already real on Earth and is actively developing. Mars will force us to rethink what food means, and perhaps these solutions will return to Earth and help solve the hunger problem here. Space and terrestrial agriculture. They are not as distant topics as they seem, and if humans remain on Mars long enough, another question will eventually arise. This is one of the most fascinating and least studied questions in all of space medicine, and it will become relevant much sooner than most people think. If a permanent colony is established on Mars, sooner or later a child will be born there. The first Martian. Or Martian girl. What do we know about this? Almost nothing. Because never in the entire history of humanity has a person been born and raised in conditions of reduced gravity. But we can build hypotheses based on what we know about the effects of microgravity on adults. Bones. On the ISS, over 6 months, astronauts lose between 1 and 2% of bone density. A child growing up on Mars with gravity 38% of Earth's would develop bones adapted to that gravity. They would be taller. The bones would likely be longer, but less dense. If that child ever came to Earth, Earth's gravity could literally break them. The bones would not be able to withstand full Earth weight. Every movement would feel heavier than they are accustomed to. Heart muscles. The heart is also a muscle. It pumps blood against gravity. If gravity is lower, the heart adapts to a smaller load. For a Martian arriving on Earth, the heart might be insufficiently trained. The brain. This is the most mysterious part. The vestibular system, which understands space, forms in early childhood. A child who grew up under Martian gravity would have a vestibular system tuned to Mars. What would happen to their perception of space when gravity changes, no one knows. And there is also the psychological dimension. This child would be a tiny planet with a name, the first representative of a new generation, like what the children of the first colonists were for the New World. They would not choose whether to be born on Mars or not. They might never see Earth or see it, but be unable to live there without serious medical preparation. This raises profound ethical questions. Do parents have the right to bring children to a planet where they will be tied to specific conditions? Is this a limitation of the child's freedom, or, on the contrary, the gift of a unique existence? These questions are currently being discussed in bioethics. For now, theoretically, but in 20 to 30 years they could become entirely practical. And here's what is interesting. If several generations live on Mars, evolution will begin to change them, not quickly. Evolution does not hurry. But over thousands of years, Martians could become biologically different from Earth humans. Taller, with different body proportions, with a different cardiovascular system. Humanity might split into 2 subspecies, and this is not science fiction. It is the logical result of prolonged isolation under different conditions. This is exactly how different human populations emerged on Earth over thousands of years. Mars is not just a new planet. It is a potential new branch of human evolution. Yet space exploration is not only about planets and colonies. In 2015, one of the greatest scientific triumphs of recent decades occurred, and although people talked about it, it did not receive the wide coverage it deserved. On September 14, 2015, 2 LIGO detectors, one in Washington State, the other in Louisiana, simultaneously recorded something incredible. They heard the universe. Literally. Gravitational waves are ripples in the fabric of space-time. Einstein predicted their existence in 1916 in the general theory of relativity, but he believed they would never be detected. The oscillations are so weak, he was wrong. LIGO detected oscillations smaller than the size of an atomic nucleus. The deformation of space-time was so tiny that it is very hard to compare. But here is a simple image. The LIGO detector is 4 kilometers long. The gravitational wave changed its length by an amount 1,000 times smaller than an atomic nucleus. This is equivalent to measuring the distance from Earth to the nearest star with the precision of the thickness of a human hair. What produced these waves? The merger of 2 black holes, each with a mass of dozens of suns, at a distance of 1.3 billion light-years from us. They were orbiting each other, getting faster and faster with every revolution, and finally merged into one massive black hole. In the final fraction of a second, this process released more energy than all the stars in the universe combined, in the form of gravitational waves. And those waves, 1.3 billion years later, reached Earth and deformed our space. They literally compressed and stretched your body by an incredibly small but real amount. Since then, LIGO and its European sister Vigo have detected dozens of similar events. Mergers of black holes. Mergers of neutron stars. This opened a new window into the universe imagined before we knew the universe only through light. Electromagnetic waves, visible light, X-rays, radio waves, infrared are all one language. Gravitational waves are a different language, completely different. They pass through everything, through dust, through gas, through black holes. They are not absorbed by anything. It is like the difference between reading about a concert and hearing it with your own ears. Future gravitational detectors will be even more sensitive. LISA, the Laser Interferometer Space Antenna, is planned for launch in the 2030s. This is a space-based detector where 3 spacecraft will form a triangle with sides 2.5 million kilometers long. It will be able to capture gravitational waves from the merger of supermassive black holes in the centers of distant galaxies. We will begin to hear the roar of the universe that until now has been completely silent to us. This is one of the most thrilling scientific achievements of our time, and when we talk about the deepest mysteries of the cosmos, one phenomenon stands above all others. No story about space can do without black holes, but I want to tell you about them not in the usual way. There's a hole in space, and it sucks everything in. That picture is wrong. Let's start with what a black hole actually is. A black hole is a region of space-time where gravity is so strong that even light, the fastest thing in the universe, cannot escape. It is not a hole. It is an extraordinarily concentrated mass. Imagine this. The sun, a star with unimaginable mass. Now shrink it down to a sphere only 6 kilometers across. In that moment, it becomes a black hole. Gravity takes over completely, and nothing, not even light, can escape. The boundary beyond which nothing can return is called the event horizon. It is not a physical wall. You would not feel anything special crossing it if you were falling into a sufficiently large black hole. But once you cross it, there is no way back. What happens inside? The honest answer: we don't know. Our physics breaks down. Einstein's theory of relativity and quantum mechanics, the 2 most successful pillars of modern physics, give contradictory answers about what happens beyond the event horizon. This is one of the biggest open problems in theoretical physics. But here's what we do know. Time in a strong gravitational field slows down. Einstein predicted this, and it has been confirmed by countless measurements. If you hover near a black hole, but do not fall into it, time for you would pass more slowly than for an observer far away. If you return to Earth after a few your hours, much more time might have passed there. This is not science fiction. GPS satellites must account for this effect in their calculations. Otherwise, navigation would be inaccurate. In April 2019, humanity saw a black hole with its own eyes for the first time. The Event Horizon Telescope, a network of radio telescopes around the world, captured an image of the supermassive black hole at the center of the galaxy M87. Mass: 6.5 billion suns. Distance: 55 million light-years. In the image, an orange ring of gas heated as it fell toward the black hole. And in the center, a dark spot. The shadow of the event horizon. People cried. Seriously, it was so monumental to see something that had only been theorized about for decades. And in 2022, they captured an image of the black hole right at the center of our own galaxy. Sagittarius A. Mass: 4 million suns. Distance: 26,000 light-years. Our home, the Milky Way, orbits a monstrous black hole. And here's what is astonishing. Black holes are not just devourers of matter. They actively participate in the formation of galaxies. When a black hole at the center of a galaxy eats too much matter, it ejects powerful jets of energy that sweep away gas and slow down star formation throughout the entire galaxy. Black holes are a kind of regulators that influence the evolution of whole galaxies over billions of years. Without black holes, the universe would look completely different, and Earth might not even exist. So after everything we've explored, rockets, planets, distant stars, and the mysteries of the universe, one final question remains. We have come a long way in the story, from the first rockets and Sputnik to dark matter and warp drives, from weightlessness and nausea on the first day in orbit to the geopolitics of the asteroid belt. I want to end this story where I began. From the window of a spaceship, there is a photograph called Pale Blue Dot. In 1990, when Voyager 1 was already leaving the solar system, astronomer Carl Sagan asked NASA to turn the camera back toward Earth from a distance of 6 billion kilometers. In that photograph, Earth is a dot, smaller than a pixel, a pale, slightly blue point in streams of sunlight. Carl Sagan wrote about this photograph, words that became some of the most quoted in astronomy. Everything we ever loved, everyone we ever knew, everyone who ever lived, all their lives were lived on this tiny mote of dust suspended in a sunbeam. That dot is our home, for now. But humanity has always been a traveler, always looked at the horizon and asked, and what's out there? And every time we found an answer to that question, a new horizon opened, wider and more mysterious still. Space is not just up there, it is our future. It is insurance for our existence. It is a mirror in which we see ourselves as we truly are, small but incredibly curious creatures who cannot stop, cannot rest, until they find out what lies around the next bend in the universe. And here's the most important thing. This journey has already begun. Not someday, now. Today, while you are listening to these words, somewhere in Florida or Texas, a rocket is being prepared for its next launch. Somewhere in a laboratory, a young astronomer is studying telescope data, and perhaps right now is seeing something that will change our understanding of the universe. And this universe is waiting. It has always been waiting. It is in no hurry. It is 13.8 billion years old. It will outlast anything we can imagine. The only question is one thing. Will we survive long enough to finally step out of our little corner and see what is really out there in that endless darkness between the stars? I think yes. And you?